The transport layer is used to set up a connection so that data can be exchanged between network devices. The two most frequently used transport protocols are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. The difference between the two is that TCP is a reliable protocol and UDP is an unreliable protocol. Let's say you want to download a full HD movie from the internet. That's about 20 gigabytes. Imagine that after 10 gigabytes, a few packets don't reach your PC. Well, once downloaded, your file would be corrupt and impossible to open. That's why in this case, we'll use the TCP protocol to make sure your download is complete. So why would we ever use UDP when TCP is reliable? Example, you're a network engineer, and you're thinking of using an IP phone solution to replace your good old analog phones. One would think that we should use reliable transport like TCP for our telephone communications. Well, that would be a bad idea, because as TCP corrects errors, this means that data that hasn't completely reached the other phone wouldn't be transmitted until all the packets have arrived. If on a phone conversation you hear something that the other person said a few seconds before, the conversation would be very strange. It's better to lose a few VoIP packets than to receive them late. That's why in this example, UDP is the most appropriate. TCP is a connection-oriented transport protocol, which means it will establish a connection before transferring data. UDP is a no-connection protocol, so it sends the data directly regardless of whether it happens. TCP uses sequencing, meaning that it numbers the packets to make sure they're in the right order on arrival. If some packets arrive out of sequence, it will hold on to them until the previous ones arrive. UDP doesn't have this feature. Here's what a UDP header looks like. It's thanks to the source and destination port numbers that we know what type of application the packet is intended for. The checksum field is a number that's added to the packet so the receiver can verify that the message received is the one that was sent. The sender runs a mathematical function on the data before sending the packet and puts this number in the checksum. The receiver runs the same function on the data it gets, then checks if the numbers match. In summary, the UDP protocol works on the transport layer of the OSI model, is a seamless protocol, which means it just sends data, still limits errors thanks to the checksum field of its header, is a protocol that provides its best effort without being reliable, and has no functionality to recover data that's been lost. Now let's look at the details of TCP. As it's reliable, it will configure a connection before you start sending data. This connection is done in 3 stages. For example, let's say PCA wants to send data to PCB reliably, so we're going to use TCP. First, PCA sends a SY synchronize to let PCB know it wants to make a connection. In our example, the sequence number, remember this is how TCP keeps track of the order of packets, is the 1. Then PCB responds to PCA, sending a message of SYN, ACK, synchronize acknowledge. It will generate a random sequence number between 0 and 4,294,967,295. For our example, let's say it's 100. And the ACK is equal to 2, which means PCB acknowledges that it's received the first message from PCA, which had the number 1, and that it's ready for the next message. And in the final step, PCA sends an acknowledgement to PCB. In our example, it sends an ACK-101, which means it recognizes the 100 sequence number of PCB. So to summarize and simplify things a little, PCA sends a TCP-SYN to tell PCB it wants to talk to it. Then PCB sends a TCP-SYN ACK to inform PCA that it agrees to listen to it, at the same time telling PCA that it also wants to talk to it. And finally, PCA sends a TCP ACK, that is, it in turn agrees to listen to PCB. Now that the connection is established, the data can be sent. We'll now talk about another feature that the TCP protocol has. This helps senders avoid sending too much data for a receiver to handle. In each TCP segment, the receiver can specify how much data it wants to receive in bytes so as not to be overloaded. Let's continue our example. PCA has established a 3-step connection with PCB. It sends 15 bytes of data. Here, the sequence number is 10. PCB responds by sending an ACK11, which could be translated as, "Thank you, I received your 15 bytes. Now send me the rest." TCP is a reliable protocol, which is why all the packets exchanged are traced. The larger the data, the higher your throughput. This makes sense because we send less ACKs than data. TCP is a fairly complex protocol, partly because its header has many more fields than that of UDP. As for UDP, there are fields for source and destination ports. These are always used to determine the type of application. There's also a field for length and checksum. But that's all. UDP headers have only 4 fields. Back to TCP. We see that 32 bits are used for sequence numbers, and just below there are also 32 bits for the acknowledgement. The flags field is where TCP defines different types of messages, such as SYN or ACK. The window size field tells how many bytes of data will be sent before an acknowledgement is received from the other side. And finally, there's the checksum field, which allows us to make sure it hasn't been lost. In short, TCP is a reliable protocol, establishes a 3-step connection before sending data, after sending a certain amount of data, uses an acknowledgement, ACK, to ensure correct reception at the other end, sends a limited number of bytes to avoid overload, and it can do replays in case of errors.